of chapter 1. So we looked at quantitative, qualitative, extensive, intensive, etc. And we're going to take it a little bit farther and look at matter here. So first thing we need to do is look at the states of matter. Okay, this is your gas or vapor. This is your liquid. And this is your solid. Now, as we look at it, the gases are widely separated, disordered particles, in constant motion. So, when we talk about gases, and we'll do an entire chapter just on gases. Most of the other things involve liquids and solids. Okay, liquids are closely spaced. And again, you can get these definitions in advance differently, etc. Disordered particles in limited motion, because remember, liquids will move around, but they won't fill the container, and gases will do that. Solids, on the other hand, are closely spaced, and they're in ordered positions. So they're ordered particles. And so we can move back and forth between gases and liquids by using cooling or heating. And then liquids to gases, cooling or heating. If you're transitioning between a liquid and gas, that's boiling point. If you're between a liquid and a gas, that's melting point. More about all of these later. But we can do a variety of things to move back and forth. But right now, we need to look at what's going on. So gas, liquid, or solid is a very critical intensive property or qualitative property associated with compounds, and we have to oftentimes, and we'll get to these in much more detail when we get to equations, we have to keep up with what's going on. Okay, so let's start back with matter. Matter by definition has mass and occupies space. So even though air didn't have a whole lot of mass, we didn't say it had to be really heavy like lead, but it does have mass and it definitely occupies space. Okay, there are two main types of matter. We have substances which have constant composition. That means they're the same throughout. They can be either atoms or they can be compounds. We'll go into detail about both of these shortly. But right now we're just trying to get the big picture. So substances are constant composition. Now mixtures, on the other hand, are a combination, and they can be a variety of two or more substances that retain their distinct identities. Okay, now that doesn't mean that they can't come together, but you can separate them by physical means when you're done. So basically, these can be any variety. They can vary from or not. And there are two varieties. We have homogeneous, and again we'll go through this in much more detail later, and heterogeneous. But what it boils down to is homogeneous means they're uniform throughout. Heterogeneous means they're not. And again, that gives them different properties, etc. So let's go through these in a little more detail. So we have atoms, and an atom is the smallest distinct particle of matter that has the properties of that element. Now, you will find as we go forward that atoms are composed of smaller species, but that is the smallest unit you can have. It's kind of like saying that you are you. If we cut off your arm, that's a part of you, but that's not you. Okay? Now, elements in general contain only one kind of atom. Now, the weird thing is, and again, we'll get to this in a minute. It can be more than one atom of that species to make the element. Now, pure elements have constant composition, physical properties, and chemical properties. Okay, that's the ditto line, by the way. Okay, so when you have an element, if it has different composition properties, physical or chemical, again, we'll get to those in a minute, then it's not the same species. Okay, so here's a little table in your text that lists the elements now in the Earth's crust and the human body, and this is by percentage. Okay, now that may be the number of atoms or it may be the mass. You actually get different values if you do it by number or by mass. Okay. All right, compounds contain more than one element. If it only has one element, then it's still an element. And they have to be combined in fixed proportions. Proportions. Oh, and by the way, if I misspell something, don't sweat it. I will try not to misspell really important words, but I'm a bad speller. Okay, molecules are the smallest, and this is important, we'll get to this later, covalently bonded particles that have, or it has, verb tense, has the properties of the compound. Now, this is important because if you have H2O, H2O is water. H2 by itself is an element, but combined it is a compound. And molecules are different than ionic compounds. I've got compound in there. The ionic compound is the smallest ratio of ions with the property of the compound. We're going to get to more of that later. But it has to do with how the atoms are attached to each other. So covalent molecules are covalently bonded are molecules. Ionically bonded are ionic compounds or salts. Okay, more about those. Again, we're going to have constant composition and constant physical properties and chemical properties. And again, if you'll notice, I tend to write in a cursive print type of motif. I will try to make it clear, but if for some reason you really don't understand something that I've written and you can't find a corollary somewhere, send me an email about it and I will share with the class. Okay. Now, here are two examples. Okay, this is water. This is really cool. If you apply a current, then you can get out the hydrogen and the oxygen gas. These are the elements. And yes, there's more than one atom, but this is your compound because it combines two atoms. Now, if it's combined, you can't just separate it willy-nilly. You can't say that that's the element hydrogen and the element oxygen. It's elements of hydrogen and oxygen combined to give you the new compound water. All right, we're back to mixtures. From sample to sample, mixtures can vary, and they can vary in composition. You can have a large amount of it, and they're going to have different properties. And they can be even different within the sample itself. Now, they're classified as two types, which is homogeneous. Definition of homogeneous means it is going to be uniform throughout. We call these homogeneous solutions, homogeneous mixtures, they have a special name called solutions. Okay, this is also known as name for them. So solutions by definition are homogeneous mixtures. Okay, heterogeneous mixtures, on the other hand, heterogeneous mixtures are going to vary throughout. Now, I'll show you an example of the figure in the text in just a minute. But if we look at it, let's say we have iced tea. Almost everybody drinks iced tea here in the South. So iced tea is a homogeneous mixture. Whether it's sweetened or unsweetened, it should be uniform throughout. If you've got a big pitcher, your first glass should taste the same as the last glass. So it shouldn't settle with time, etc. Now, heterogeneous, on the other hand, is, let's go with ranch salad dressing. Because ranch salad dressing has the white stuff, you can do the Thousand Island or any dressing pretty much, and the little pieces of the spices, etc. So it depends upon which drop you get as to what it has in it. And especially if it's homemade and it's not mixed well, then every bite may be different. All right, and here we go. This is heterogeneous. And a lot of times you can look at it, and so like if I put a little circle here, I don't really have any black, but if I do the circle here, I have a lot of black. So just looking at different parts, I have different species. Now, this is copper 2 sulfate, and this is copper 2 sulfate in water. And once it's mixed, if you'll notice, it's uniform throughout. So this is homogeneous. Blue on blue doesn't work, does it? Homogeneous mixture here, so this is a solution. So most of the time, it's really easy to tell the difference of things. Okay, this is another figure from a Pearson text, and I just like it because for those of you who are visual, you can start with the matter. Is it variable? If no, it's pure substance. If you can separate in simpler substances, compound. If not, it's an element. Over here, if it's variable, it's a mixture. Are we uniform throughout? That would be homogeneous, and no would be heterogeneous. So you can see it's everywhere. And again, it's something that you can easily use all the time. It's just not a matter of vocabulary. Chemistry is a 2 for class. It's an applied math class, and it's a language all of its own. Biology, the same thing, except for the math part. They don't do as much math in biology, but it's a language of its own. And so if you treat it as a foreign language and you see a term and you don't know it, you need to make sure you understand it so that you can, when you hear it, know exactly what it means. If you don't do this, it makes your life a little bit on the miserable side. Okay? So some of the problems in the text are very good. They're going to walk you through the problem, and then they're going to walk you through the answer in detail. I highly recommend the problems in the text. From the back of the book, you have problems in the back of the book, and a lot of times I will take problems either really close from the text or verbatim from the text and use them in the test. Because the more problems you work, the better you're going to do. And so a lot of times the problems in the back of the book are very similar to the ones I post. And I do have extra problems with keys posted, as well as videos of extra problems besides the ones we're going to work in the lecture. So I'm not going to work this one, but I do want you to go look at it. It involves gold and what the difference between, for example, white gold, rose gold. Well, they didn't do rose gold, but they did white gold, and what it actually means. Okay, but I've got some problems too. This one says classify each of these as to the type of matter described, whether it's an element, a compound, or mixture. So we have sugar, which is a compound, dissolved in water, which is a compound. So we're having two compounds, so this has to be a mixture. And water does dissolve in water, and sugar does dissolve in water, and as long as there's no solid present, then it's probably homogeneous. Now, if you left sugar at the bottom, then it's heterogeneous. Okay, we have soda pop in the can of carbonated beverage. Okay, wait a minute. This one is not as simple as the previous one. We have soda pop, which that's some sort of mixture because there are all kinds of flavors in there. And it's carbonated, which means you added CO2. So if you look at a glass of Coke, carbonated beverage, pick your poison, in the glass, and you look at it, we know it's a mixture, that's a given. Is it homogeneous or heterogeneous? Well, if you think about it, it is heterogeneous. Why? Because some places you have those little bubbles. Okay, these are bubbles, or they cause bubbles, assuming it's not flat. Then you have a heterogeneous mixture. Now, before they add the carbonation and they just have the Coke syrup, like if you're working at a fast food restaurant and can see that whole thing, they're going to add the CO2 to it as well as some extra water because they concentrate it. Then you will get the carbonated beverage out. So it is a heterogeneous mixture. Now, use motor oil freshly drained from a car. When back in the dark ages, when I was growing up, everybody changed their own oil. We don't do that anymore, but I'm betting some of you have. And if you look at it, when you drain the oil out of your car, you want to look for particulate matter. The more particulate matter you have, that's a bad sign for your car. So if it's used, it's going to be, well, whether it's used or not, it's going to be a mixture. But if it's used, it's going to be heterogeneous because pure motor oil that you pour out of the can is uniform and it would be homogeneous. But once you've passed it through your car, if you pour it in, you usually get particles settling on the bottom, so that makes it heterogeneous. Okay? A diamond is forever. No, actually, diamond isn't forever. Graphite is. Diamond is actually a form of carbon only. That makes it an element. And the comment about the graphite is that's a different form of carbon, and that one's actually slightly more stable. So over time, diamonds will go to graphite, but it takes millions of years and or a lot of pressure. So you're good on your diamond. Okay, a 25-cent coin. We call that a quarter. And everybody's like, oh, a quarter is uniform. No, it's a mixture. And is it homogeneous or heterogeneous? Well, if you tilt it on the side and you look along the side of it, and I'm going to do a bad drawing of the side of it here, okay? So if you look at it, usually you'll see copper in the middle. And there's used to be silver on the side, but it's usually nickel now. And so you have a combination, so it is heterogeneous. Okay? So it is a mixture and it is heterogeneous. Now, a single crystal of sugar. If you've ever eaten rock candy, That is basically a humongous big crystal of sugar. We know that sugar is a compound. And if that's the only thing you have, it is a compound. It's not a mixture because it's by itself. Okay, so that brings us to the next properties, which are physical properties and chemical properties. Well, physical properties are a characteristic of the sample matter without changing its composition. Okay, that's things like distillation. I'll show you some examples. Boiling, that's boiling something off. You can use something as simple as a magnet if you're removing something that's magnetic. Sand and steel shot, you can use a magnet and remove it all. It doesn't change the composition, it just separates them based upon some sort of physical property. Now, chemical property, on the other hand, undergoes a chemical change. So, for example, if you have HCl plus sodium hydroxide, then this is an acid, this is a base, and when you're done, you've got a salt and water. I'll give you a hint. This is the 4-letter S word for an ionic compound. And if I could make that go away. Okay. So that would be a chemical composition change because it's different. Another example is when we'll keep with the salt. So sodium chloride is necessary for a biological system. If you don't have any sodium chloride in your system, your different cell channels don't open and close, so you're dead. Okay, if your sodium and your chloride content are too low, you're dead. If it's too high, then in some cases it causes hypertension, which is a really big name for high blood pressure. And some people it doesn't affect at all. Again, that's personal, etc. But you have to have that to survive. But if you were to either eat sodium, metal, or chlorine gas, both of those will kill you dead. Those are toxic to you. But they're totally different forms. They are chemically different. So they have different properties and etc. But they have different chemical compositions, and so they have different chemical properties. Okay, so here are a couple physical changes. This is simply filtering out. This is something yellow. I'm assuming sulfur and water. And so the filter paper will stop the sulfur from going through. You do that easily with sand. This here is distillation, and which is a fancy way of saying using the boiling point to separate compounds. This is chromatography. Which is color writing, if you translate it out in Roman. But it separates it based upon its different properties as it goes through different solvents. And maybe more about that later. That might actually be a cool lab for y'all to do. Hadn't thought about it, but we'll move on from there. But all of these are ways to use physical changes. So you're not actually changing the compounds that are involved. You're just separating from one another. So you have sulfur and water here. You end up with sulfur and water here. You haven't changed anything. This is not the same thing as burning a stick or something. Okay? This is a chemical composition. This is nitric acid, HNO3, and it is an acid. And you can take a coin here, and this is the copper. And the copper is going to be dissolved, and so what you end up with here is copper ions in solution. And this is actually a noxious gas. This is NO2, I think. It's either NO2 or N2O4 gas. And so when you're done, you don't have copper and nitric acid. You have totally new species. So this is definitely a chemical change. And I don't recommend you playing with nitric acid concentrated. Weak nitric acid will clean it without dissolving it. You really need it concentrated, and there are only two concentrated acids that really scare me. It's nitric and sulfuric. So be very careful if you're dealing with any of them. Okay, so identify each chemical or physical property listed in each statement, and also identify the underlying information as intensive or extensive. Okay, so the overall statement is we have a 15.3 gram sample of azulene is blue and melts. We did not change the azulene compound with anything. We did melt it, so that's a physical change because we changed its physical state. Okay, and then we need intensive or extensive. Well, this would be intensive. No, see, there I go reversing things. Okay, to what extent it is there. So this is extensive. Blue doesn't matter how much we have, so that's intensive. And melting, that means that's an intensive property. It doesn't matter if we have a lot or a little of azulene, it's all going to melt at that temperature. It may take longer if you have a lot, but it's still that temperature. Okay, copper filings are put in a fire and burned with a green flame. This is true, and this is actually really cool. Later, towards the end of the semester, I'll show you what the copper flames look like. So overall, this is actually not changing the copper. Excuse me. We're going to burn it. So when we're done, the copper combines with oxygen and you get copper oxide. So since it's burning, this is a chemical change. If I could spell chemical, there it is. Okay. Filings, that tells you what the shape is. If you don't know what a filing, think about something that's grated, like grated cheese. That would be cheese filings. They don't call them that because that sounds weird. But so that would be an intensive property because it's describing it. Green flame, again, that would be intensive. You'll see later if you play with this that in lab that the more copper you have, the more intense the flame. And so we've covered that one. So this one is first one is a physical change, second one is chemical change, and C is the white crystals of table salt or cubic. That is a physical property. So if we're talking about a change, we could change it from a cubic to dissolving it and letting it get like, what is that candy? Rock candy. So it could be all over the place. So this is a physical. Okay, and if it's white crystals, again, that's intensive. Intensive. Again, spelling is optional here. And since I can't spell and you can't spell, the rule of thumb is when you're answering questions, if your spelling is close to, it's okay. This is not true when we get to naming, and I'll make that very clear. Cubic is a shape, so again, that's intensive. Propane gas burns in the heat of the combustion reaction is used to 3-minute boil an egg. Okay, well, gas burns, that's chemical. Oh, I'm squaring the properties. Boiling an egg is another chemical because you can't get it back. If you can't get it back, it's usually, well, it's always chemical. In terms of, you can't get it back because you can't capture it, that's different. But if you could get it back, then it's physical. So we're said the heat of combustion. Now, the heat of combustion is an intensive property because, and we'll get to that intensive later when we do calorimetry, but that is a function of what you're dealing with compound wise and how much of it you have. So how much of it is the extensive, but what you have would be the intensive. Okay, and this is a 3-minute boil of an egg. And you're like, okay, 3 minutes. That's what's called a soft boil. I don't like them that way. But a lot of people like their eggs soft boiled, so that is critical that you only do 3 minutes, so that is extensive. So to what extent do you boil it? If you boil it longer, it's no longer soft. So you don't get what you want. Okay? Sodium metal, when dropped in water, causes an explosion. This is actually true. And creates sodium hydroxide, a base. So we're going to start with sodium. And we're going to go to sodium hydroxide. No, you don't have to know what they are. You will later. But so this is definitely a chemical change, because we have gone from an element to a compound. Okay, this is an element. This would be a compound. Okay, and then the question is a base. Well, what's a base? Well, we haven't gotten to what a base is, but basically a base is a property, so that would be intensive. Okay. Ethanol is a colorless liquid that vaporizes easily. 3.4 milliliters of it boils at 78 degrees and has a density of given. Okay, did we change the ethanol? Nope, this is all physical. Because what it's doing is listing the boiling point, which is the vaporization, and the density. So colorless liquid would be intensive. And usually numbers are extensive, but vaporizes is, actually that should be underlined, vaporizes easily. That's intensive. Because that didn't say vaporizes with 15 grams of heat or whatever. 15 kilojoules of heat. Grams is not. 3.4 milliliters, that is an amount. That is extensive. So usually if you have numbers, it's going to be an extensive because it's giving you amount. And then we have the density. Wait a minute. Density is one of those sneaky things. It's a number, but is intensive because it doesn't matter how much ethanol you have, the density is the same. It's like syrup. Syrup, whether you have a little bit, a lot of it, is thick and sugary, right? So that doesn't matter. That's a density. And we'll get to density in one of the next components. Okay, but so what we were able to do here is to identify statements as to whether they were physical or chemical changes. Now, to kind of put it all together, we have one last problem. We have a black powder in a long glass tube, and we've passed hydrogen gas through it, and the purpose of that is to sweep out other gases. Then we're going to heat it. And then once it heats, the powder turns orange red, and water vapor can be seen condensing at the unheated end of the tube. Okay, when the red orange color remains after the tube cools. Okay, so the question is what is the original black substance and element? Well, we took I'm gonna call this I was gonna call it BS, but we'll call it B. Let's just call it B. So we took B. We know we added hydrogen gas, and we know we ended up with water plus something orange, red orange. Okay? So if we had just had an element, we would have only ended up with one compound. So since we ended up with more than two, then the answer to this is probably no. It had to be a compound because we produced more than water. And because we know that the B had to contain oxygen plus unknown materials. So, no, it was a compound of some sort. Then the next question is the new red-orange substance an element? Maybe. Don't know. It could be, and it also could be a compound. We do not have enough information to make that prediction. If I had given you more information, you might be able to, but right now, with the information given, I'm not taking that bet. I can think of a couple elements that might be considered orange, red, orange, but I can't think of many. But that doesn't mean that these people aren't colorblind and made of color. Anyway, but I don't know. I don't know enough information. So in this case, it's a maybe. When I ask you questions on a test, I try to avoid the maybe questions. We'll do the maybe questions together because I need you to think about stuff to make sure you know what it is you're doing, per se. But on test situations, don't overthink them. Okay? I promise you that it will be a much more cut and dried question as opposed to something like this, because you could go either way on this one. All right, and that brings us to the end of this section.